See.
I would have thought.
Okay, Chapter 6, the last chapter in this unit, deals with metabolism. So we're going to look briefly at some of the laws of thermodynamics and then hopefully end today talking about ATP and why ATP is used as an energy currency in cells. So there's a section in here that I absolutely hate teaching, and it's about Gibbs free energy, and I'm sure you will cover it in Mr. Rourke's chemistry class as well. So it's like my least favorite section. Yeah. But anyways, talking about thermodynamics. Thermodynamics just means the study of heat and how it's transferred, but cells are governed by the laws of physics and chemistry, and one of them is thermodynamics. And so the laws of thermodynamics, there's 4 of them. So the first one is energy is conserved, and it can change forms. It can be converted, but it's conserved. So it's very similar to like the law of conservation of mass. What we call this one, the law of conservation of energy.
Sandy O'Leary, come to the office, please. Sandy O'Leary.
Second law deals with how energy tends to flow and then tries to reach equilibrium. We'll also talk about entropy with the second law of thermodynamics. And then won't really touch the third law, but it's just a driving force of just like defining this. And then they were like, oh crap, there's a fourth law. Let's just call it the zeroth law. Thermal equilibrium is transitive. And again, we're not going to cover that, but we're going to focus on the second law mostly. So, and the first one, I lied. We'll talk about these two.
Why can't it be called the fourth law?
I don't know.
Because it's
It's so weird.
Okay, so the flow of energy. We know that energy can take many forms, and it also has many definitions. And so the broad or the basic definition of energy is the capacity to do work. If it can do work, it's most likely using energy. There is 2 states of energy. You have your kinetic and your potential. So hopefully physical science 9, these terms are ringing a bell. Kinetic means energy of motion. So if it's in motion, it's using kinetic energy. Potential energy means that it's like at rest. So maybe it's elevated, it's stored energy. It could be elastic or a spring, but it's stored and it has the ability to do some work. And so here the car is moving up the hill, we're using energy, there's this kinetic energy, but then it gets converted to potential energy for a brief second, and then it goes back down and it's moving again, kinetic. You throw a ball up into the air, and there is a moment where it's like at rest at the top, potential, and then it gets converted back to kinetic. This little flow chart talks about, like potential, so like chemical, gasoline, all you gotta do is just like start the combustion process and it takes over from there. You have gravitational potential energy, electrical potential energy, nuclear, as well as elastic. So those are all forms of potential. For the kinetic side, electrical can be motion too, because then once you actually, flip the switch, you have a flow of electrons. Sound, because of vibrations, okay, there's motion there. Thermal, because of kinetic motion of particles. The faster they move, the more thermal energy you have. Wind, and even light. So lots of different forms, shapes that energy can take. So yes, many forms. Mechanical energy, heat, sound, electric current, light, even radioactive radiation. But the primary way that we tend to measure all this energy is heat. And so thermodynamics just means heat changes, or studying heat. The unit of heat in biology is the kilocalorie. Okay, so 1 kilocalorie equals 1,000 calories. And to even give you a definition of what 1 calorie is, it's the heat required to raise the temperature of 1 gram of water 1 degree Celsius. A lot of times in nutrition, if you read the nutrition labels, they give you calories, and that calorie is the same as a kilocalorie. Okay, so I'm just going to say, how many calories are in your Monster drink? 110. So yes, in nutrition 110, but it's also 110 kilocalories. Okay. No, it says it's actually the same as a kilocalorie.
What And why is 1
Also
kilocalorie
calories
a
in
thousand?
nutrition.
Yeah, in nutrition. So on the food
Oh.
label, it's a kilocalorie.
That's actually like a million
Yeah. Well,
calories or thousand.
take it times 1,000. So 110,000.
Wait, but why are they?
Why are they different? Could you imagine writing 110,000 calories?
Well, yeah, but
I think it has something to do with Americans just being stubborn. Because, you know, like, I don't want to say kilocalorie. That means we're kind of like metric. Let's just
I
call it a
suppose.
calorie. So stubborn. So, that's my personal, I don't know. I really honestly don't know. I think it's probably a good question to look at. There is another unit out there that you can use to measure heat, and that is the joule. And to give you a perspective of how small the joule is compared to a calorie, it's 0.239 calories for 1 joule. I always tell my kids that you want to do 1 joule of work, you have an apple, which Jessica Badhauer just brought in, so I guess I could demonstrate this, but I'm not going to go to my house and grab an apple. But you have an apple at the waist, and you just bring it to your mouth. You just use 1 joule of energy. Yeah, you're actually you're burning many joules per second. I think it's like over 100 joules per second. Just sitting there at rest. Okay. You can trace all the energy back to the sun, and so the sun does provide energy for all the living things, living systems. Estimated the sun provides Earth 13 times 10 to the 23 calories per year, or 40 million billion calories per second. That's a big number. How we use that energy, we have our photosynthetic organisms that capture that energy, and then they convert it into sugars. So it converts carbon from inorganic to organic form, because carbon dioxide, yes, it has carbon and it has oxygen, but we can't use this for energy. So technically we could call it an inorganic molecule and then convert it into organic. So stores that energy into covalent bonds, and then we eat the sugars. Remember, nope, never mind. I've never said this to you. My biology 10 kids, I've said this to. In order to break bonds, it's the same amount of energy to form that same bond. So to break a bond between carbon and hydrogen takes 98.9 kilocalories, but if you wanted to reform that bond, it takes the same amount of energy.
98 moles.
Are you guys doing that right now?
6.02
Yeah.
times 10 to the 23rd.
This also ties into our oxidation reduction reactions, and it actually is more related to Chapter 6 than what it was in Chapter 2 with chemistry. But, you know, when you transfer electrons, bonds are being made and broken. And so remember, oxidation is loss of electron, and reduction is gain of electron. Don't forget that. Maybe on this actual exam there will be a question about oil rig. I know I said it was on the exam, and then I looked at it. I was like, oh, I must have been thinking about this exam. My bad. So. Okay, the laws of thermodynamics do govern all energy changes in the universe. So the first one, energy cannot be created or destroyed, but it can change from one form to another. Okay, so you guys eat food, okay, and we also give off body heat, but then we also give off some waste products like water vapor, carbon dioxide, and then, you know, whatever we can't digest, that's another form of waste. So all that energy that we took in, you know, is being transferred into different forms. We're a great example of that. The amount of energy in the universe remains constant, but it can change different forms, bounce back from one form to the other. In any living organism, chemical potential energy stored in molecules can be shifted to other molecules and stored in different chemical bonds. And like I said, can be converted to other forms. So we usually take a glucose of molecule, or yeah, a molecule of glucose, and we break it down into CO2 and water. And we're converting it into a different molecule with different chemical bonds. So this diagram, I think, does a great job representing that, where you have all the energy before, but then notice they have some shaded regions saying, oh, it got transferred into something else. But the energy is still the same. It's still at the same size box, but it's just different forms. And it's a scale, so it's balanced. Okay, during each conversion, some of the energy dissipates into the environment as heat. And so remember our definition of heat, the measure of random motion of molecules. You can harness heat to do work, especially if there's a temperature gradient, meaning, you know, hot to cool areas. However, cells are way too small to use heat as a source of energy or to do work for them. So a lot of times we just lose this energy as heat. So and that's actually a problem in engineering. Building an engine where you can, whatever work you put in, you get more or, the same out, but you always lose some to friction. You always lose some to heat. And so there's always that goal of trying to build a combustion engine that's whatever you get put in, you get the same back out, basically. Okay, second law has something to do with something called disorder or entropy. So it says that some energy is lost as disorder increases. And so we call this disorder in the universe entropy, and it's always continuously increasing. You want to put things back into order, you got to burn some energy. So I always like to think of my bedroom or even my house right now with my little child. So my daughter, I have a lot of books. Books. I just love books. And my daughter will go through and she'll just and take them off the bookshelf. And then I come home and I'm like, and then it takes energy to put them back. Okay, and then the next day, same thing. Or like your bedroom. You clean your room and then life just gets crazy. And then all of a sudden you look at your room and like, how the heck am I living in this? I need to clean. Okay, so like entropy, it's very easy for it to increase. So disorder is more likely than order. It's more likely that a column of bricks will tumble over than the pile of bricks to rearrange themselves spontaneously to form a column. We call this usually like the time arrow. Energy transformation goes from spontaneously to convert matter from a more ordered form to a less ordered but more stable form. It's like disorder is just gonna happen. It's just the way the universe works. So we call this entropy. Increases when the universe formed. It held all the potential energy it ever had, and it just has become progressively more disordered ever since. And so this kind of also ties in with like Big Bang Theory, or like how the universe forms. Are we expanding? Are we collapsing? Well, it's most likely expanded just because entropy always usually increases. So some comics. I just feel that our relationship's entropy has increased. I really want to hear that. Second law of thermodynamics with entropy. Block of ice is more organized because the atoms are actually arranged in the crystal lattice structure. And then as you increase that entropy, now you get a puddle of water. But then to make it ordered, it goes back to a block of ice. Here's talking about the bricks. It's just more likely that a column of bricks will tumble over and just become disordered rather than spontaneously building that column. Here we have a highly ordered solid. Okay, see the separation, but molecules move and disorder happens, and now it's mixed. So chemical reactions can be predicted based on changes in free energy. So remember, to break bonds, it takes energy to break bonds. That means you have to increase heat, which means atomic motion also increases, and it's just easier for atoms to pull apart if you can, heat something up for the chemical reaction to start. Kind of goes back into, I think I had a picture of magnesium, and then I put it in helium. Was that this class? I don't know. But okay, so like if I had magnesium ribbon and I just put it in helium, which is a noble gas, inert gas, nothing's going to happen. However, if I put it with oxygen and then give it a little heat, something's going to happen. And I see a brilliant, bright light. Don't look at it directly, basically. So free energy is the energy available to do work in any system. It's basically your net energy after breaking and forming bonds. So with free energy, I guess that's on the next slide. Anyways, here's the second law of thermodynamics: energy before, energy after. There's some forms of energy that you just can't use, and that could be like that heat or that friction.
So will the Earth have the universe have a lot of energy?
No, it's infinite. It's just being transferred from one form to another. I mean, like stars die, like our sun will explode, but then it will start all over again. So after it blows up and shoots out all the atoms that are in it, gravity will take over, bring it back in, condense, and reform a new star. So stars just kind of like reincarnate into new stars.
But wouldn't part of it, like if it went far enough, wouldn't it, the gravity help some different stars?
Oh yeah, it might, yes. Because I'm sure that when our star goes, it's going to engulf like Mercury and Venus. So there's going to be other stuff mixed into it.
Yeah,
Mm-hmm.
it probably won't be too good for Earth either.
Nope, definitely not. Okay, so with that free energy, we call that free energy Gibbs energy, or it's represented by capital G. It's equal to the energy contained in a molecule's chemical bonds, and we call that enthalpy. So don't get enthalpy and entropy mixed up. Entropy is disorder, enthalpy is chemical energy and bonds. So you have your enthalpy minus your entropy times temperature in Kelvin. So do you guys know how to convert from Celsius to Kelvin?
Oh, isn't it just that one of them starts at 0?
Yeah, one of them starts at 0 and one
The
starts
other
at
one starts
273.
at negative.
Yep. Okay, so you just add or subtract 273. I don't know which way you're on.
Which one is, which one is, Celsius starts at negative? No.
Celsius starts at 0.
Yeah.
No,
No, because
Celsius
0 is the
negative.
freezing point.
Yeah,
Celsius,
Kelvin starts at 0. It's absolute 0.
yeah, and Celsius starts at negative. Because 0 is the freezing.
And that gives you the
Well,
free
isn't
energy.
0 and Kelvin
Yes.
absolute zero?
Kelvin is absolute. It's based on absolute 0. So 0 in Kelvin is minus 273.15. So degrees Celsius. Thank you. Yes. There we go. I think for your test, you don't have to like actually plug in numbers, but you do have to understand like, what if I increase enthalpy? What will happen to entropy if G remains the same?
There'll be
So, yeah, so you'll just have to like think about that relationship. Okay. So I hate the word free energy because it's not really free. It's just like what's there. So I like the term available energy better with Gibbs. And so does anyone know what the delta symbol mean in science? Change. So that's the change of energy or the difference in energy. So it's the available energy that's left. Because remember, it's kind of like your net energy. Spontaneous reaction means if you give it a push, it will go on its own. So if I have a tennis ball at the top of the slide and I just give it a push, well, it's going to go on its own. So it went from potential to kinetic. If I have a semi-permeable membrane, kind of like what we've talked about with osmosis and diffusion, it's going to move from high to low. And then those are cherry bombs. If I were to light one, just give it a little nudge of energy. In this case, a match. Your chemical potential energy will be converted. Yes, that potential energy will be converted to kinetic. Okay. So let's talk about some, different relationships looking at this system with the slide and the tennis ball. And so the question is, what's going to happen to our total energy, H? And H is enthalpy. Okay, so let's focus on the enthalpy of the system. Potential energy is greater at the top than at the bottom, right? Okay. So to look at just the enthalpy of the system, it's greater at the top than it is at the bottom. So notice my big H versus my small h. So H is decreased, and you can think of potential energy in living organisms as like the bombs that have the ability to break and release energy. Questions about this system just looking at enthalpy? It's pretty simple, right?
enthalpy.
Mm-hmm.
Is
Total energy of a system.
that's the one that's measured in the Gibbs curve.
It's in the equation for Gibbs. Okay. Let's look at entropy with diffusion, because that's just a great example of that. So here I have my semi-permeable membrane. You remove the membrane. What's going to happen? Molecules are going to move. They're going to spread out. You're going to increase your disorder. If I were to remove the walls, I'm going to get a big mess. So even more disorder. So the typical pattern that entropy tends to follow is that it increases over time. A little less, it's nice and ordered, and then chaos happens. It's bigger. Questions about that? Yes? Okay. Okay, cherry bombs. If I were to put a cherry bomb on your desk, would it explode right then and there? No. But if I applied a little bit of heat, in this case temperature, or struck a match, well, I'm going to increase my temperature. Chances are it's most likely going to explode. I do have a great story with those pop, like those,
Ones you throw on the ground.
yeah, what are they called? I don't know. But the ones that are just like wrapped up in paper and you throw them on the ground and they just make that pop.
Yeah.
So I played basketball at Gustavus, but we had a summer league in the cities in Minneapolis. So I had to drive from Benson to the cities like every weekend to play in this league. And we took turns carpooling. So like there were some other people in the area that went to Gustavus and played basketball. So we took turns carpooling to save on gas. And so I picked up this real country. She was very country, just very polite girl. And we're driving through downtown Minneapolis. And as you drive through downtown Minneapolis, you start to see, the neighborhood changes. You go from, like, I don't want to say rich white, but all of a sudden, then all of a sudden you kind of hit, like, the Hispanic, the Hmong. And then we got into the heart of Minneapolis. And some, pretty heavy African-American population, okay? So we're stopped at a stoplight, and this was the weekend after the 4th of July, so I had some of those on my dash. And my friend was like, oh, what are these? And we had the windows down because I didn't have AC, and it was super hot. And I go, oh, those are like firecrackers. So you like throw them at the ground, and they make a sound. So on the corner of the stoplight, there's a bunch of guys just sitting there, And she takes it, and she throws it.
Oh, God.
And all of a sudden, pow, pow, pow. I got scared. I mean, these guys were, whoa, whoa, and they like whipped out a handgun, and they start, what are you doing? I'm like, oh my gosh, and I'm like, the light turned green, and I just peeled out of there because I thought I was gonna get shot, and I'm like yelling at my friend, I'm like, are you crazy? And it's like, she didn't think, she just did not. It's just a completely different environment for her. So
Minneapolis?
downtown, yep, it was the downtown YMCA, like just,
Yeah.
woo.
It's not real rich on there.
Yeah, I'm scared. Okay. The entire time. I was like, shit. All that adrenaline rush. All right. Going back to Gibbs free energy and what this really means. If you were to get a delta G as a positive, that means you have an endergonic reaction, or maybe in biology, an endothermic reaction. Maybe that term rings a little bit more bell. It's the same thing, endergonic and endothermic. They're the same. But basically, your products contain more free energy than the reactants. That means that your H is higher, or maybe your S is lower. So that's what I mean by the relationship. Cannot proceed spontaneously until you get energy put into it. If your delta G is negative, that means it's going to release this free or available energy. And so that is exergonic or exothermic, if that's a term that means more to you. So your products contain less energy than the reactants. The H is lower, or the S is higher. So it's like a seesaw. So just think about those reactions. I kid you not, I'm sure I'm going to have a question that says, G is positive. Like, why is it? And I'm going to have options like H is higher. And then I'm going to just really mess you up and say, like, S is higher. So you, like, have to really think about it. Okay, so
S is higher, that would make it there less.
well, I was just, like, giving you that's the incorrect answer. This would be the correct answer. Yeah.
I thought you were asking me.
No, that was not, I'm just saying, like, that could be an example of a test question. Okay, so anyways, H is lower, S is higher. It can proceed spontaneously if it's different in disorder or, some discrepancies there, but it does release that available energy. So I think this slide kind of sums it up real nicely, where if you get the exergonic, what's less than energy being released, cellular respiration is a great example of that. And then if it's positive or greater than 0, whoops, I was supposed to have 0 there. It's endergonic, it requires energy. Photosynthesis is a great example of that because it absorbs the sunlight. And then if your delta G is 0, then it's equilibrium.
So ender requires energy input,
Mm-hmm.
and exer gives off energy.
Gives off the, yeah. Yep. So again, this diagram just kind of does the same thing. Just looking at like maybe the energy input of different solutions or whatever system you're looking at. But I just really like the delta G is negative exergonic reactions. And so it shows the chemical equation where the big arrow on the top means it's going to proceed and actually happen, but it is reversible. But in this case, because it's exergonic, it will proceed in this direction. In endergonic, that means you need energy for it, or G is positive, so it's going to go from the products back to the reactants usually. They're like, they're opposites of each other. So if you know one system really, really well, then you can just infer opposite for the others. Does that make sense? That might help you, because then you just got to know one type of reaction really well.
So is that like the proton?
Yep. So on that previous slide, you saw arrows going in both directions. Chemical reactions are reversible. So if it's exergonic forward, it's got to be endergonic in reverse. So you saw that the arrows changed sizes in the directionality of it. If it's at 0, that means the arrows would be the same size, pointing in opposite directions. So that's equilibrium constant. Okay, this is a graph showing exergonic versus endergonic reactions. And I am doing this right now with my biology 10, and I'm not sure if Mr. Rourke did or if Mr. Lash does this with you. But if this is like the energy that the reactants have before, and this is the activation energy, the amount required to get that energy going, and then it takes off, and then the products, they have lower energy than where it started, well, this energy drop is the energy that's going to be released. So this is a graph just showing you, what's going on with the energy. Instead of just giving you numbers, there's a nice visual representation. So the products have less energy than the reactants. Energy is released. The reaction occurs spontaneously. Remember that your entropy will increase because of that energy being released. With endergonic, that means you need energy into the system. So this is the energy that all the reactants had beforehand. You get that activation energy, it overcomes it. But then, however, the reaction happens, but it ends right here for energy. This difference from where it started to where it ends is the energy supplied or absorbed that it needed. So your products have more energy than the reactants. Energy is required. It's not spontaneous because you need energy and your entropy decreases. So again, another comparison slide. But like I said, if you were to just learn one of these really, really well, then you could just infer the opposite for the other. So I drew AE for activation energy. And so that's what I want to talk about right now. I lost my words. So in order for a chemical reaction to occur, you usually need an input of energy, and that is called activation energy. And what this energy does is it allows the chemical bonds to be broken, and the rate of this exergonic reaction depends on the AE. So if you have a high activation energy, the rate will be more slowly because it has to overcome all that initial energy. You can change the rate of the reactions by lowering the activation energy. So one way to do that is you can increase the heat, or you can add a catalyst, like your enzyme, with the liver lab. So in our liver lab, our catalyst was called catalase, and it was found in our liver, and it takes H2O2 and breaks it down into water and oxygen. Well, H2O2, given enough time, will spontaneously break down into these parts. That's why hydrogen peroxide has an expiration date. Because eventually, and it's in a brown bottle to block out heat, okay? But we have enzymes inside of us that make this, that do this chemical reaction more quickly. Because we don't want to wait around for a month to break down catalase. It wouldn't serve us any good. We'd be dead. So catalase lowers the activation, and as a result, activation energy, as a result, reaction happens more readily, right before your eyes. Boom, boom. So I want to talk a little bit about cellular respiration and photosynthesis, because I said those were great examples for endo and exogonic or thermic reactions. And so with cellular respiration, you are taking glucose and oxygen, okay, and you're going to basically do a combustion reaction inside of your cells. So this process, it's more random. You're going to release energy, breaking glucose down into carbon dioxide and water vapor. The Gibbs free energy, or the delta G, is a minus 686. And so because of that minus sign, that means it's exergonic energy is being released. In photosynthesis, it's the opposite. You're taking, water and CO2, and you're making a big molecule, glucose. You're taking all these random bits and pieces, and you're making it more ordered, but the energy involved in making it more ordered is positive, so 686 kilocalories, because we're still making and breaking the same types of bonds, but it requires the input of energy, in this case sunlight, and it's an endergonic reaction.
So you're adding 686 kilocalories.
Yes, it's absorbing. Yep, so you're adding energy to the system.
Oh, okay.
And the other one is given off, so you can use it. So catalysts, what they do is they try to lower the activation energy. So if you didn't have an enzyme, this is the hill, basically, that you would have to overcome to get the reaction started. But enzymes make the hill smaller. So you guys took a bike trip last year. No hills, right? I heard it was brutal. But
Oh,
there's a
hill.
There's a little hill.
I missed it because of the goat.
Oh, nice. But anyways, if you had to, climb a massive hill, that would just suck. But when you get to the top, you get to coast. That's pretty fun. Well, what that enzyme would do is just make this hill a little bit smaller. So you're like, oh, it's not as big as it could be.
But the drop is still.
The drop is still, you'll still end up at the same place, bottom of the hill. So catalysts or enzymes, they influence chemical bonds and the flow of the reaction, but it does not violate any of the laws of thermodynamics. So it just lowers the activation energy and increases the rate. It's not used up in the law of conservation of mass. They're just there. It is reusable. You saw that with your enzyme lab, that you could pour things off and redo the experiment with what you had, and it refoamed again. So it does not alter the proportion of the reactants or the products. You can reverse the process as well. So enzymes are really important in biological systems, and so we call enzymes usually catalysts. The term is used interchangeably. Okay, the last section I want to talk about is ATP, and that is the energy currency of cells. ATP stands for adenosine triphosphate. So this is the adenine and the sugar, ribose, bonded together. This is the adenosine part. This is the triphosphate. And this last bond between this phosphate and this phosphate is a little bit unstable. It's very easy to break, and it does release energy, and you can put it back together. So ATP is just the ideal currency for energy inside of cells to carry out life processes.
So when that last bond breaks apart, it's ATP.
Yes. Yep. So cells store and release energy in bonds of ATP. So the structure of ATP, you have a 5-carbon sugar called ribose down here. You have adenine, which is a nucleotide. And so that's another, if you remember from our chemical evolution, you have to be able to make nucleotides spontaneously in order for life to make DNA. So maybe you remember that ribose RNA hypothesis, maybe not. It's okay. And then a chain of 3 phosphates. 1, 2, 3. So there are other energy carriers that your cells can use, and so we will talk about GTP and cellular respiration. But there's TTP, UTP, CTP. To tell you the truth, I don't know what any of these mean, so sorry. But GTP, I believe, is guanine.
I feel like they all end in triphosphate.
Yeah, they all end in triphosphate.
What was the C? Is the U the uracil? The T the thymine? The C
Oh,
the
you're absolutely,
cytosine?
yes, there it is. Good eye. All right, some other energy carriers. 2 phosphates, 2 organic phosphates bonded together. This is a intermediate molecule, I believe, in glycolysis, or I think these are both in glycolysis. So you will actually have to memorize 1,3-bisphosphoglycerate. So what is it? Bisphosphoglycerate. This? Yeah. It's just an intermediate molecule of glucose being broken down. Oh. and modified. So yeah, we'll talk about that in cellular respiration. Okay, so how ATP stores energy, it lies within the 3 phosphates. Phosphates are highly negative, and so if you have 3 negative ions or phosphates, they're obviously going to try to repel each other. And so due to this electrostatic repulsion, the covalent bonds are unstable, and they're really, really unstable between the last 2 phosphates. So the hydrolysis of ATP is negative because energy will be released. So if you break this bond, energy is released, and that energy can be used to do work. So bond breaks, releases energy. And then you can reform ADP plus P to form ATP. So it is reversible. So now you're left with ADP and an inorganic phosphate. And then if you use a little bit of energy, in this case, in the process of ATP synthase, you can recreate ATP. Cleaving off the phosphate group on the ends becomes adenosine diphosphate plus an inorganic phosphate. This liberated phosphate temporarily binds to intermediate molecules, and then when it's dephosphorylated, it's released as an inorganic phosphate.
Wait, is the ATP adenosine or?
And sorry, do I keep saying adenosine?
Well, no, right there it
It's
said
adenine.
adenosine. But I'm saying, like, is it adenosine and ADP and adenine and ATP?
Oh yeah, yes, yeah. But I think I use it interchangeably.
Wait, so
I'm really
ADP
sorry.
is adenosine and then ATP is
Adenosine, but it doesn't matter. You just need to know ATP, ADP. I'm not going to say what does that mean, and you have to spell it out. That'd be terrible. Okay, ATP hydrolysis drives the endergonic reactions. So we use ATP to use it to carry out processes. So here's my ATP. I cleave off the last phosphate. This energy is fuel for other processes the cells have to carry out. But your cells can create ATP again, like the process of cellular respiration. It is recyclable and reversible. So here's the breakdown of Gibbs. To go from ATP to ADP plus B, minus 7.3, so it's exergonic, that's energy being given off. And then to create ATP using that inorganic phosphate and ADP, you gotta use a little bit of energy. So it cycles continuously. Most cells only have a few seconds supply of ATP, so it's gotta do this all the time. ATP can be cyclical, because you have one part of your cell doing exergonic and another part doing endergonic to keep your supply steady. So, yeah, that's it. Cool. All right, so tomorrow I'll lecture Chapter 6, Part 2. Yeah, lab Thursday, Friday.